Let's get right into it. Number 7. Time dilation makes GPS satellites lose 38 microseconds daily. Let's start with something that actually messes with your daily commute, but not in the way traffic does. GPS satellites, those little space beacons that help you find the nearest taco joint, are orbiting Earth at roughly 14,000 kilometers per hour. And thanks to Einstein's theory of relativity, they experience time slightly differently than you do on the ground. Specifically, their clocks gain about 38 microseconds every single day. That's 38 millionths of a second. Sounds tiny, right? But if left uncorrected, that tiny drift would accumulate into a GPS error of about 10 kilometers per day. Imagine your Maps app telling you the taco place is in the next county. And because relativity says both speed and gravity warp time, the satellites have to adjust for both their high velocity, which slows time per special relativity, and the weaker gravity up there, which speeds it up per general relativity. Net result, 38 microseconds faster each day. So next time you complain about GPS lag, remember we literally had to rewrite the laws of physics to get you that burrito. And the satellites don't even have to deal with HOV lanes. Number 6. Quantum entanglement allows particles to instantaneously affect each other across the universe. Imagine you have two magical coins, flip one in New York, and the other in Tokyo instantly lands on the exact opposite side. No delay, no signal, no nothing, just pure spooky action at a distance. That's quantum entanglement for you, except it's real and it works on particles, not coins. When two particles become entangled, they share a single quantum state. Measure the spin of one, and you instantly know the spin of the other, even if they're on opposite sides of the galaxy. Einstein called this spooky action at a distance because it seemed to break the cosmic speed limit. Nothing can travel faster than light, right? Yet somehow, entangled particles exchange information faster than you can say, that's impossible. Now, before you get too excited, no, you can't use this to send faster than light messages, because the outcome is random. You can't control what the particle decides to be. But the correlation itself? Pure magic. Scientists have tested this over hundreds of kilometers, and the universe just shrugs and says, yeah, that's how it works. It's like finding out that everything you thought about distance and time is just a suggestion. Next time you lose your sock in the dryer, just remember, somewhere there's a quantum entangled sock that knows exactly where yours is. Good luck finding it. Number 5. A spoonful of neutron star weighs 6 billion tons. Okay, picture this. You're at the cosmic buffet, and you decide to take just a tiny spoonful of dessert. But that spoonful weighs as much as Mount Everest, or actually as much as all of humanity combined, plus a few dinosaur skeletons. A neutron star is what happens when a massive star collapses and crushes its core into a sphere about the size of a city, but with the mass of 1.5 suns. The gravity is so intense that atoms themselves get crushed. Electrons merge with protons to form neutrons, hence the name, and matter becomes so dense that a single cubic centimeter, about the size of a sugar cube, weighs roughly 100 million tons. So a spoonful? That's about 6 billion tons. If you tried to pick it up, you wouldn't just fail, you'd be instantly flattened into a thin paste of subatomic particles. The teaspoon would punch through the Earth's crust like a hot knife through butter and head straight for the core. But don't worry, you'd be dead before you even touched it. Fun fact, neutron stars also spin incredibly fast, up to 700 times per second, and emit beams of radiation like cosmic lighthouses. So maybe just stick to regular ice cream. Your back will thank you. Number 4. Quantum tunneling lets particles pass through solid walls. Ever been walking and suddenly realized you're on the other side of a locked door with no memory of opening it? No? Just me? Well, quantum particles, electrons, protons, the works, do this all the time. It's called quantum tunneling, and it's exactly what it sounds like. A particle can basically walk through a wall. In the quantum world, particles behave like waves. When they encounter a barrier, they don't just bounce off. Part of their wave can actually penetrate the barrier and emerge on the other side. If the barrier is thin enough and the particle has enough energy, or just a little extra from nowhere, it can appear on the far side without ever climbing over or digging through. This isn't theoretical, it's the principle behind the scanning tunneling microscope and even nuclear fusion in the sun. Without tunneling, our sun wouldn't be able to fuse hydrogen atoms at its core because the repulsion would be too strong. But thanks to tunneling, protons just slip through. So next time you bump into a wall, imagine you're an electron. You could be on the other side in a quantum blink. But you're not because you're a macroscopic bag of meat that follows boring classical physics. Sorry. Number 3. Black holes can evaporate through Hawking radiation. Black holes, the universe's ultimate hoarders, they suck in everything: gas, dust, stars. That one astronaut who yelled, "No take, only throw," and nothing ever escapes. Right? Wrong. Stephen Hawking figured out that black holes actually leak. Slowly, very, very slowly. Thanks to quantum effects near the event horizon, particle-antiparticle pairs pop into existence all the time. Usually, they annihilate each other and vanish. But if one of them crosses the event horizon, it falls in while the other escapes into space. To the universe, it looks like the black hole just emitted a particle, and since energy must be conserved, that particle's energy comes from the black hole itself. Over time, the black hole loses mass. It shrinks, evaporates. For a solar mass black hole, this process takes longer than the current age of the universe, about 10 circumflex, 67 years. But for smaller black holes, it's faster. Eventually, as the black hole gets tiny, the evaporation accelerates into a final burst of radiation. So black holes are not eternal. They die, which means the universe has a deadline. But don't stress about it. That deadline is so far in the future that the stars will have burned out, galaxies will have dissolved, and the universe will be a cold, dark wasteland. But hey, at least the black holes won't outlast us. Wait, that's not comforting at all. Number 2. The Heisenberg uncertainty principle means you can't know everything. You know those nosy people who want to know exactly where you are and what you're doing at all times? Quantum particles find them exhausting. The Heisenberg uncertainty principle says you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know where it is, the less you know about how fast it's moving, and vice versa. It's not a limitation of our instruments. It's a fundamental rule of the universe. You can't cheat. Even God can't know both, and Einstein hated that idea. He famously said, "God does not play dice with the universe." But quantum mechanics just shrugged and kept rolling. This principle isn't just philosophical, it has real consequences. For example, it prevents atoms from collapsing. In an atom, electrons zip around the nucleus. If they had both definite positions and momenta, they'd spiral into the nucleus and all matter would implode. But thanks to uncertainty, electrons are forced to maintain a cloudy, fuzzy existence, which keeps atoms stable and you from turning into a puddle of goo. So next time someone tells you you're being uncertain, tell them you're just following the laws of quantum mechanics. It's not your fault the universe is fuzzy. Number 1. The double-slit experiment proves particles are also waves. We saved the most brain-melting for last. The double-slit experiment is the granddaddy of quantum weirdness. It's simple. Fire a beam of electrons at a barrier with 2 slits. If they were particles, you'd expect 2 neat piles behind the slits. But instead, you get an interference pattern, like waves passing through both slits and interfering with themselves. So electrons act like waves. Fine. But then scientists set up detectors to see which slit each electron goes through. Suddenly, the interference pattern disappears. The electrons behave like particles again, as if they know they're being watched. This isn't about consciousness, it's about measurement. The act of detecting which slit destroys the wave-like behavior because it forces the electron to have a definite position. Without measurement, the electron exists as a wave of possibilities, passing through both slits simultaneously. It's in a superposition of states. Only when you look does it choose a single reality. This means that on some level, reality is created by observation. The universe is not objective, it's participatory. You, by simply looking at a thing, change what that thing is doing. So next time you trip over a coffee table, blame it on quantum superposition. It was both in your path and not in your path until you observed it. You made it real, and then you hit your shin. Congratulations. That's all for this video. I will be making similar kind of video in future. Subscribe to stay updated.